Did I record this? I did. Now, normally we use limits to find derivatives, don't we? So when we use the first principles and all that, we're looking at the limits as h gets smaller and smaller and stuff like that. But Hoptails rule is a bit funny because it uses derivatives to find limits, but only in certain cases. And this is what Badai kind of made an error with yesterday. You seem to know it, Badai, but it doesn't always work. It only works when we have an indeterminate form. That's what we need when we apply the limit. So, and the indeterminate forms that we look for are 0 over 0, infinity over infinity, or something like that, or even 0 times infinity. They're all indeterminate form. Remember, something like 0 over 2 is not indeterminate. That's just 0. And 2 over 0 is also not indeterminate. It's undefined. It's impossible. This is just something that's not clear. They're okay for answers. So the technical way it's written is perhaps, well, unnecessary to know, but we'll look at it anyway. When it's written, it's like limit when x approaches a constant or a number. For fx over gx. If the limit as x approaches c of the fx function, so hopefully you come across that, is 0, and the limit as x approaches c of the gx function is 0, or it could be infinity over infinity, or negative infinity over negative infinity, or whatever. If it has these traits, and the limit of their derivatives approaches something, so p, for instance, then we can also conclude that the limit of the original function, we don't have to prove this rule, it's beyond the course, so we can just take it as is also p. So let's say the limit approaches 6 of the derivatives, then the original one also approaches 6, as long as it's indeterminate in the original form. Okay, so that's technicalities. It's far better to look at it in principle, or in working. So let's look at an example. And I presume if you've watched any videos on the internet or anything, you've seen examples of this. Let's just look at a very simple example. The limit as x approaches 0 of, so I'll ask you, what's the limit of this? Of sine x over x. So first of all, we need to determine, is it L'Hopital's ready? Is it L'Hopital? So let's test. So what's the value of sine x as x approaches 0? At 0, yeah. So limit is 0, and the zeros as x approaches 0 is just, the limit is just 0. As x gets to 0, it is 0. Okay, so therefore, yes, it's indeterminate. So we can apply L'Hopital. So that has to be your first test to make sure you can apply it. So therefore, I need the derivative over the derivative. So let's look at the limit of the derivatives as they approach 0. So the derivative of the top is, the numerator is cos x, isn't it? And excuse me, the derivative of the denominator is, well, the derivative of x is 1. So now we test it as x approaches 0. As cos approaches 0, it approaches 1, and we should know that from our unit circle. As cos approaches 0, the angle approaches 1 because it approach here. And 1 is just 1, so therefore we now have a new limit 1. And once again, you could graph that on your Desmos, and perhaps if you've Desmos there, have a look at sine x over x. And I have it up here on screen. So there's sine x over x. As x approaches 0, it is not approaching 0, it approaches 1. You can see that. It here is 1. So it's coming to 1. Cool. Not 0. All right. Right, so let's look at a more difficult example. And the next example is a classic one. And I'm going to get... well, I'll walk through it, perhaps. So I'm going to look at the limit as x approaches 0 of 2 sine x minus sine 2x all over x minus sine x. So, Dustin, are you there?
Yes, sir.
What is my first step? What do I need to do first here?
I'm not sure.
Okay, so I need to test, is L'Hopital's rule, can I use it? If this has a limit value straight away, that I can just look at it when I evaluate it towards 0, then I don't need to do L'Hopital's rule. It has its limit. We know it already. So,
so
this is, yeah.
If you don't need to apply L'Hopital's rule, that means like we already know the limit.
No, if you can test the limit at this stage, and if you get an actual value that it's tending towards, that's its answer. It only works when you don't get an answer. When 0 over 0 or infinity over infinity, these are indeterminate. They're not answers, satisfactory answers.
Okay.
So you're trying to find, is it a non-satisfactory answer?
As x approaches 0.
Yeah. So does this give a satisfactory answer or a non-satisfactory answer? So you need. Okay. So why? Well, because sine of 0 is 0.
And then...
So 2 times 0 is 0. Minus, well, 2 times 0 is still 0. So sine of 0 again is 0. X is 0. And minus, well, sine of 0 is 0. So we're at 0 over 0. Okay. Yes, now we can use L'Hopital. But if that was something different, if that was the number 6 over 1, or, even 0 over 2, that way you can't use L'Hopital. Okay.
But if it does give you 0 over 2, what can you infer with that result?
The limit is 0. It tends towards 0. 0 over 2 is okay. And 2 over 0 is undefined. It won't exist. The limit.
But 0 over 0 is not undefined, right?
Yeah, no, it's not undefined. It's indeterminate is the word for it.
Okay.
Okay. So you're looking for 0 over 0 or infinity over infinity. This is very likely to come up in a non-calculator paper. So in paper 1, due to the fact that if it was a paper 2, you could just stick it into the calculator and you can have a little look at it, what answer you should get. And we'll look at this on the calculator in a second, but we're going to go use L'Hopital's first. So L'Hopital, Dustin, what would I have to do next? Or are you still kind of a little bit lost with this one at the moment?
Yeah, still a bit lost, sir.
Okay, so Badai, what would I do next? I'm going to apply L'Hopital.
Yeah, don't you have to derive the numerator over gx?
Yeah, so I have to derive the numerator and the denominator.
The denominator, yeah. So it's f dash x over g dash x.
Yes, exactly. So that is L'Hopital's rule. Get the derivative. So you've tested it at its limit. It is going to be L'Hopital. Now you need to get the derivative of the top and the bottom and test it again. So that's L'Hopital, Dustin. So you test first. And if you get something like this, you derive the top, derive the bottom, and test again. Okay? So let's derive the top. Rigel, can you call out the derivative of the numerator, please?
Cosine or two cosine.
Yep.
Minus cosine 2x times 2.
Yes, so use the chain rule when it's like this. This is a function kind of within there. So it's going to be the cosine of the function, I suppose, times the derivative of what's inside, and derivative of 2x is 2. I'm going to put that in front, though. But Dai, can you derive the denominator, please?
1 minus cosine x.
Yes. Okay. Next step, Badai.
You plug in 0 for x.
Okay. So, what's the cosine of x? Or zero? Sorry, the cosine of 0.
That's gonna be 1. So 2 minus 4.
Let's just check. So, subbing this in first. So 2 times 0 is going to be still 0.
All right. So it's just minus 2 again.
Yeah. Okay, and we get 1 take away, and that's going to be 1. Yeah. Cosine of 0 is 1.
So it is indeterminate.
That's 0 over 0 again. So do we stop?
Do we do another derivative?
Yeah, we keep going, because this could have been the original question, of course. If this was the original question, you would have done it. So you've tested the Hoptails rule for this function and still get it, and we go on again. So
How many times do we test this, sir?
until you get a satisfactory answer.
Oh, so you can end up doing it up to like 5 times, for example.
Yeah.
Are there any questions that do not have a satisfactory answer? Or
No. I think every question would have a satisfactory answer. Any question you would get in the exam would have something that I wouldn't imagine you'd go beyond the Hoptails 3 or 4 times. I think 4 would probably be as far as you get, but you could keep applying it. It might go around in circles. I'm trying to think of an example that might go around in circles forever. Leave that with me. That's a great question. I need to come up with an example for you. There probably is examples that the Hoptails rule will go on forever and never give a satisfactory answer.
Like -1 to the power of n times cosine or sine thing. The powers keep on switching.
So you're saying, sorry, say that example again.
I don't know, something with sine and then like -1 to the power of like some variable.
Yeah, that wouldn't be a function then, would it?
Yeah.
No. So for this, I was thinking e to the x, because e to the x derives to e to the x. So that would go on forever. But of course, if it's over e to the x, they would cancel each other out. So it'd be just 1. But something with e to the x might be it, or the ln x or something in it. Leave that with, I'm sure. I'll just Google it now, sure, since we're here. Even though the conditions for how it must be met is indeterminate. Again, apparently there's not many. E to the it is one with e in it. It's e to the -1 over x squared. Apparently, I'm not entirely sure. That is not in the form at the moment that we need it. Leave that with me. I'll do more research onto that one. I'm not getting an answer straight away, so you're not going to get one that doesn't. Well, high. Maybe in paper 3 you might get something that's a bit more tricky like that. But we need to get an answer here. Far more likely that something like this will come up. Okay, so let's continue on with this. All right, Dustin, you're up for the derivative of the numerator.
Oh, no. Is it? Is it 2?
So we're deriving cos x. No, it wouldn't be 2. What's the derivative of cos x?
Is it sine?
Mm-hmm. Negative sine, yeah. So there's going to be negative 2 sine x. So that's from your formula booklet. So this is also going to be a sine. Let's make sure I get this right. There's going to be still 2x, isn't it? But the
It's
derivative...
Plus 4.
It's going to be 4, but because that cos has gone to minus, that's minus minus, so that's a plus, yes. I think that's right. Correct me if I'm wrong. Derivative of 1 is nothing, so that's gone finally. And derivative of negative cos x is going to be negative negative sine x, so that's just sine x. Okay, test again here. Speed things up. We know sine x is 0, so that's going to be minus 2 times 0, so that's 0. Plus, well, that's still 0. 2 times 0 is still 0. Oh no, over 0. Maybe if I get this, no, that's still going to be 0. Uh-oh. So that's 0 over 0. We need to go again. X equals 0. Get the derivative again. Let's speed this along. I'll do it this time. So derivative of this is just going to be minus 2 cos x again. And this one now is going to be, okay, it's going to be 4 times 2, which is 8. And it's going to be still stay positive because it's sine to cos. And it's still going to be 2x. And then that's going to be over cos x. Evaluate this now. Remember, cos of 0 is 1, so that's minus 2. This is plus 8. And finally, we have an answer that's satisfactory because this is 1, isn't it? And that is now 6. Now, let's have a little look at Desmos and let's make sure that that makes sense. I have to
Wait,
check.
sir, so when we have the result as 6,
Mm-hmm.
what does that tell us? Like, what does it mean to have an answer of 6? Is that like
Rigel, perhaps you can explain. Do you understand what it means?
That there is a limit.
And it is at limit.
Oh, so as x approaches 0, it approaches y equals 6, you mean?
Well, we hope so.
Okay, I get it.
We'll have a little look now. If not, we've got it wrong. X, I'm just doing it, typing it in here, and then I'll let you look. And I'll get rid of that one. And look at that. So as it approaches 0, so you can see here, where is it? As it approaches 0, it is approaching 6 for both sides. That's kind of cool, isn't it? We got there after using Hoptails rule 3 times. First, so the steps Hoptails rule would be the same each time. First test, do you get a limit? If you get something at this stage, just by looking at it as it approaches infinity or whatever, it's usually 0 or infinity, you'll get 0 over 0 or infinity over infinity. If you get that, if you get anything else, then there's no need for Hoptail. A bit like the example you were looking at yesterday, but you had an answer, so therefore you didn't need to apply it.
Yeah, we already know what the limit is.
Yeah, you're already know. There's no point in going any further. And you can always, if you're saying, is this correct, graph it. You know, if you're practicing, definitely just graph it. All right. Let's give you guys.
So how can we graph something that's approaching in? Oh wait, never mind.
Yeah, so it'd be maybe an asymptote or something like that. Yeah. Okay. I've done this. Okay, so let's give you guys one and see who can get the limit of this one first. I'm going to use one with e to the x in it, actually. I'm going to use limit as x approaches infinity of e to the x over x cubed. So I want you guys to do that one now and see, can you get an answer? When you have an answer, just shout out.
It's just infinity.
Yep. So hopefully the other two, you're getting to that point. But if we try it at this point, we get e to the infinity over infinity cubed. That's infinity over infinity. So yes, we can use L'Hopital. So I'm going to do this a little bit quicker. Just the derivative here. I'm not going to write the limits. Remember, here is still e to the x. This is 3x squared. Test it again. It's still infinity over infinity. Infinity squared is still going to be infinity. But you see that the denominator is getting smaller and smaller as you derive, isn't it? And that's still infinity over infinity. And then your last one then, e to the x over, then when I derive that, is 6. And that's going to be infinity over 6, which of course is infinity. Hopefully that made sense. So that's a satisfactory answer. We got something. Infinity divided by 6 is still going to be infinity. And it's still infinitely large. So hopefully you followed that. Okay, what about, we'll do one more.
Wait, but sir, if it's infinity over 6,
Mm,
does that
yeah.
mean like, oh, x approaches infinity, y approaches infinity then? Right? Like it's increasing forever.
Yeah, as x approaches infinity, the y will go towards infinity. Yeah. So you can have a little look at that if you want to sketch it on Desmos. I just want to do one more with you. You guys do this one, and I'm going to do another x towards 0. It's going to be another trigonometry one. Okay, off you go on that one. Let me know when you have an answer.
Isn't it? It just, you don't need to use it, no?
It's 0, sir. No, it's like I got 0 over 1.
Yeah.
You don't need to use it.
Don't have to, cannot use it. So it's 0 over 1, which is 0. And you can have a little look at that on Desmos. Let's have a little look at that before we finish. So x plus sine x divided by x plus.
Sir, if we're supposed to use L'Hopital's rule in implicit differentiation, do we also have to do as y approaches a constant?
To use L'Hopital's rule during implicit differentiation?
Yeah, like not
what
just
do you
x, also use y, right?
How would you do that?
I'm not sure. I'm asking.
No, you wouldn't be able to use it
Okay.
unless
So-
it's separated. Unless you can you'd have to separate it. If it's separatable, a bit like the answer, if it's separatable and it's put into, if it's two functions then separate of x, yes, you could use it. But if it's not two functions separate of x, you can't use it. So you're not going to be asked to during implicit. That would be beyond.
It would always be like in a shape of a circle, right? If it has a y.
No. It would come back on itself at some stage.
Right, so it wouldn't be a function because
yeah, it's not a function, so we can't use it.
Yeah. Okay.
But sometimes you can, if it looks like one, you can separate it into one that is, it might be a function, it might look like a implicit, but you can separate it. As long as it's y equals 2 and then it's just x on the other side, then it's possible. But often when the implicit usually is, it's something that can't be separated. That's why it's implicit. Let's have, just to finish off, let's have a little look at those two questions we just did, just to make sure we're correct. So this is the first one we did, the one that was, we said approaches infinity. Of course, often the temptation is infinity over infinity to call it 1, and it's not, as this is getting bigger and bigger, going towards, as x goes towards infinity. So you can see that it's shooting off there towards infinity, and that makes sense. It's not going down towards 1. Of course, infinity over infinity is not 1. And the second example then, x over sine x. So you guys said that it does have a limit as x approaches 0, and it is 0. And you can see that it goes through 0, 0. You can see that on the screen. It goes through 0, 0, so that's all good. It does have a limit. And you didn't need to apply the Hoptails rule. All right. So I think that's us. I need to finish up. What I'm going to do is, you have maths, I think, on next. We're missing. You don't have it tomorrow. We're going to not see you until Tuesday, I think. Is that right? Yes. Oh no, we don't see you until Wednesday. That means you're going to be set a bit of work, a lot on the Hoptails rule, and then a little bit of work over applying applying differentiation, so related rates and stuff like that, bit of chapter 19, see how you get on. And that's going to be due on that Wednesday, so that's nearly a week away. Let's have a look. I can't remember. Yeah, and then you have your practice exam on the Thursday. The notes for the practice exam do include the Maclaurin series, but I'm not going to ask you the Maclaurin series in this exam. So that will come up in the next exam. So that's the only thing from that list that I have. So hopefully you see that's the list of stuff that's on Manage Back in for the practice exam. Everything is going to come up in that besides the Maclaurin series. So what we're going to look at next Wednesday in that double period is going to be related rates questions and optimization questions. So, but I'm going to give you a few of them beforehand that you can look at, and some of the Hoptails rule that you can look at, and we're going to look at them on Wednesday. Thursday then is the practice test, and the following week is your actual exam. Any questions, comments, or are you all okay?
Sounds good.
Cool. So I'll post that work on Manage Back in the next half hour or so, and then I'll see you on Wednesday.
Thank you, sir.
All right. See you guys. Bye.
Thank you, sir.